Section 2.3, Negations of Quantified Statements. So our goal for this section is to determine how to negate universal, existential, and universal conditional statements. So how do we negate a quantified statement? Let's consider this statement here. All snakes are poisonous. So a lot of times when I ask students, oh, go ahead and find the negation, a lot of times students will say that the negation is no snake is poisonous. And this is actually incorrect. The correct negation ends up being this here. Some snakes are not poisonous. Remember what the negation does. Your negation has to have the opposite truth value, right? So if we start out with this statement up here, all snakes are poisonous, we can say that this is false. So when we negate it correctly down here, some snakes are not poisonous, that becomes a true statement. Notice the incorrect negation, this one here, no snake is poisonous, that's still false. So that's not the proper negation. So logical equivalence for quantified statements. Logically equivalent quantified statements always have identical truth values no matter what predicates are substituted for the predicate symbols, and no matter what sets are used for domains of discourse of the predicate variables. We're going to go over a couple of theorems. Negation of a universal statement. The negation of a statement of this form here for all x in D, P of x. This is logically equivalent to a statement of this form here. There exists an x in D such that not P of x. Symbolically, if we are to negate the universal statement, so I have the negation in the front here, that's going to be equivalent to this statement here. There exists an x in the domain such that not P of x. So in other words, the negation of a universal statement, all are, is logically equivalent to an existential statement. Some are not, or there is at least one that is not. The second theorem, negation of an existential statement. So the negation of an existential statement of this form here, there exists x in D such that P of x, is going to be logically equivalent to a statement of this form here. For all x in D, not P of x. So symbolically, if you have your existential statement here, and we're negating it, so I'm putting the negation on the outside, the negation of an existential statement is logically equivalent to this universal statement. So in other words, the negation of an existential statement, some are, is logically equivalent to a universal statement, none are, or all are not. So a really easy way to help you negate statements is to use this little table here. So this is your guide for negating quantified statements. So if this here is this first column is the form of the statement, the second column is the form of the negation. So if we have a statement that starts out all are, then when we negate it, it becomes some are not. If we have a statement that says none are, when we negate it, it says some are. If our statement form is some are, the negation is none are. And if our form of the statement it has some are not, then the negation will have all are. So for that first statement we looked at briefly in this video, it was an all are statement. It said all snakes are poisonous, and the correct negation is that some snakes are not poisonous. So let's use that table for this first example. We're going to write informal negations for the following quantified statements. So for part A, we have some cars are red. So we have some are. So you're going to look at your table. Some are is down here. And negation is going to be none are. So if I have some cars are red, the negation is going to be no cars are red. And you can kind of check the truth values too. Some cars are red, That's true. No cars are red. That's false. And then for part B, we have some dogs are not furry. Some are not. Go to your table. Some are not. That's at the bottom here. And the negation involves all are. So some dogs are not has the negation, all dogs are furry. So if you say some dogs are not furry, okay, we could say that's true. And then if we negate it and have all dogs are furry, then that's a false statement. And then the last one, part C, no history class is fun. So no. That would be like the second row here, none are, no class. And then the negation involves some are. So if we say no history course is fun, the negation would be some history courses are fun. And then no history course is fun. That's probably a false statement, right? At least for me, it would be. I took a couple of history of math courses in college. So then the negation, no history course is fun, if that's false to me, then the negation, some history courses are fun, becomes true. Example 2. Now we're going to write formal negations for the following quantified statements. So for part A, we have all dogs D, for all dogs D has a collar. So this is an all statement, so it has to be turned a universal statement, so it has to be turned into an existential, some are. So this is going to be, there exists a dog, D, and then D has a collar, so we're going to say such that D, and then we're negating this here. So this is like a, for all X and D, P of X. That's the current form. So if we're going to negate it, think back about the theorems we went over. If we negate this, that becomes there exists X and D such that not P of X. So I'm negating this part has a collar. So I'll say such that D does not have a collar. So that's your negation. These are going to be a little bit more challenging because you can't really use not really using that table exactly. So think of the theorems and maybe have that in front of you when you're doing the homework. And then for part B, there exists a computer C such that C is a Mac. So right now, part B is saying there exists an X in D such that P of X. So if we negate it, that's the current form of part B. So if we negate that, that existential statement is going to be logically equivalent to a universal statement for all X and D, not P of X. So you're changing for these, if you're changing like this one here, it says D has a collar. So you're negating that. D does not have a collar. But at the same time, you also have to switch over your quantifier. So the for all became there exists, an existential, when you did the negation. Same idea in part B. So we're going to switch this C is a Mac. That will become C is not a Mac. But we also have to remember to switch over the quantifier also. So the existential becomes a universal. So we'll say for all computers, C is not a Mac. So be careful when you're doing the homework for these, especially when they're in formal form and you're writing a formal negation, because a lot of times what I'll see students do, they'll negate this part, they'll negate the D has a collar, the C is a Mac, they'll remember to negate that, but a lot of times they'll forget to switch the quantifier. So just be mindful of switching that quantifier as well as part of the negation. And then you have the negation of the universal conditional statement. All right, this gets even a little bit more involved. So you have to recall from chapter 1, when we did chapter on symbolic logic, we went over the conditional statements, and we went over how if you negate the conditional statement, it was logically equivalent to a conjunction. So it is false that if P then Q is logically equivalent to P and not Q. And we actually use that fact here with the quantifiers. So if we are negating, here we have our negation in the front, we're negating a universal conditional statement because you have your if then there. So again, your universal part becomes an existential, but the conditional if then becomes the conjunction between P and not Q. This will be one of the more challenging ones. Example 3, write formal negations for the following quantified statements. So for part A, we have for all integers d, if 8 divided by d is an integer, then d equals 4. So the first thing we're going to do for this to negate it is to change over the quantifier. So we're going to say there exists an integer d such that. And then this conditional if then, if this is like the p of x here, and this is your q of x, then we're going to have our p of x, 8 divided by d is an integer, and not q of x. So d does not equal 4. So we're changing that if then, that conditional, into the conjunction of p and not q. Let's see about part B. For all real numbers x, so that's going to become there exists a real number x such that if x is greater than 2, then x squared is greater than 4. So we'll say x is greater than 2 and x squared is not greater than 4. And this part here, you can leave this like this, or if you want to rewrite this and say x squared is less than or equal to 4, that's fine too. Those are equivalent, so you could do it either way. Okay, now we're going to do part C. This is going to be the most challenging of all of these. So this part here, it says for all x in the set of real numbers, capital R like that, that stands for the set of real numbers. If x times x plus 1 equals 0, then, there's your conditional, x equals 0 or x equals negative 1. All right, this part right here, that's together with a disjunction. So the first thing we're going to do is start by negating, changing over your quantified statement so that the for all becomes an existential. So there exists x in the set of real numbers. And you can also, if you want to, you could just say there exists a real number x. You can write that out. You do not have to use the set notation now because we're going to have a whole other chapter that's just going to go over set theory, and you'll end up using that notation then. So if you want to just write this out and say x is a real number, that's fine. Such that, all right, now here's where it gets interesting. You have your if then, right? So let's say this part here, that's like your p of x, right? This part here, after the then, is your q of x. So we know that this is going to have to be p of x and not q of x, right, when we do the negation. Okay, so I'm going to write down the p of x part. Nothing's happening with that. That stays as it is. The if then gets replaced with the disjunction, conjunction, the and conjunction, so I'll say and And then right here, in order to negate the or, you're actually going to use De Morgan's law. So the Q of X part, this part right here, this is like P or Q. And so when you go to negate that, like we went over in the first chapter, to negate this disjunction, De Morgan's law tells us that we end up negating the statements and then changing the disjunction to a conjunction. So when we write this out, so this is a little bit harder because there's not just one statement over here, you have like a compound. So you're going to write and x does not equal 0 and x does not equal -1. So that right there, this part right here, that's this part. And that's De Morgan's laws from the previous chapter. You'll see this again in like the homework or something. So make sure you're careful and you see when you have more than just a conditional going on. And then I have a couple notes to finish up this section. So vacuously true universal statements, those are the true by default. Consider this statement here. No cars in the parking lot are red. The statement is false if and only if the negation is true. So the negation is there exists a car in the parking lot that is red. If the parking lot is empty, the negation is false. And so the original statement is true by default. And then we're done with this section. Try the homework, and then I'll see you in the next video.